Okay, let's give a shot at the reflection principle. Okay. Okay, so let's go through this. It's only a page of notes, so sort of practice as well to get used to this new format. So we got one result, the reflection principle, in this section. It relates to a type of symmetry of an analytic function. I stated it as theorem 2.28.a in the notes. And the reflection principle states, suppose that a function f is analytic in some domain D, which contains a segment of the real axis and whose lower half is the reflection of the upper half with respect to that axis. Then f of z bar equals f of z bar for each point z in the domain, if and only if the function's real when the input is real. Now, the stuff about domain D, domain's an open connected set. So we've got an open connected set which contains a segment of the real axis, so it intersects the real axis in some segment, and it's got a symmetry with respect to the real axis. The domain has a lower half that is a reflection of the upper half with respect to the real axis. So a disk with its diameter lying along the real axis would be an example of such a domain. More often than not, we're going to deal with functions that are entire, so we'll be dealing with an entire complex plane. And certainly the reflection principle will apply to those kinds of domains. Now, the condition f of z conjugate equals f of z conjugate. Remember, when you conjugate, you're, for say z itself, replacing the imaginary part of z with the negative of the imaginary part of z. And geometrically, that corresponds to flipping things about the real axis. So the claim here is, if we put in a reflection about the real axis of a point z, then the function values have that same type of symmetry. So I put in a point z conjugate, and we get out the conjugate of f of z. So it's a certain type of symmetry, and it's symmetry with respect to inputs about the y-axis, as well as the outputs about the y-axis in the w plane, as we've called it before. So the claim is we get this type of symmetry, this type of equality to hold, if and only if inputting real values output real values. That is, if f of x is real for any point x on that segment of the real axis mentioned above. So the details on the domain and its symmetry are probably fairly easily satisfied for what we'll consider. So as long as we're talking about functions that have real inputs that produce real outputs, then we've got the reflection principle going for us. And we still don't have that many functions, but some of the functions we'll have will be polynomials, exponentials, sines and cosines, hyperbolic sines and cosines. All these functions, if we have real coefficients in the polynomials, we certainly have real coefficients in the power series for the exponentials and the trig functions, then these are examples to which the reflection principle applies. That's basically the content of the next note. It says, notice that any polynomial with real coefficients, complex variable, real coefficients, a sub k, we have that P is an entire function. Okay, so the domain is the entire complex plane. It satisfies the symmetry on the domain as mentioned above. It's real. P of x is real. For x real because all of the coefficients, all the a sub k's are real. So we have the symmetry satisfied on the domain. We have P of X real for X real. That implies by the reflection principle that we have this type of symmetry here. This P of Z bar equals P of Z bar. Yeah, this follows for just, we could take conjugates of this little polynomial up here and plug Z bar in, and we could deduce that as well. We move to power series representations for functions, and then it's not quite so easy because series are limits, not just sums. When we develop more functions, as I mentioned, like exponentials and sines and cosines, the other trig functions, the hyperbolic trig functions, they'll all fall into this category. Probably the functions you're familiar with before this class starts, and that's roughly a list right there. Those functions satisfy the reflection principle. An example of a function that doesn't satisfy the reflection principle, all I've got to do is throw in some imaginary numbers in the formula to, in a sense, for the function. If we take f1 of z equals I times z, that won't satisfy the reflection principle. Plug in anything real, take z real, and that's going to produce I times z is purely complex. So it's not going to satisfy the reflection principle. It won't have the symmetry. It's not real when you have real inputs. And similarly, down here for, say, a second function, f2 of z equals z plus I, same problem. You put real numbers in, you don't get purely real numbers out. You get complex numbers out with non-zero imaginary part, because the imaginary part will be I if we input a real z. So not all functions satisfy the reflection principle, but many of them you are familiar with. They do. So I'll bring that to an end, and we'll move on to the next section.